I think my talk, the title is the innovative method for large-scale fingerprint identification system, which is also the title for my thesis. So in more or less, I would like to report what I have done during my PhD program. So this is the agenda for my talk. So the first, I will give a short introduction about what is the biometric system, and then I will describe some research aspects in a fingerprint identification system. Then I will introduce what we have done from 3 perspectives. The first one is the finger photo quality assessment. The second one is the fingerprint indexing, and the third one is the security enhancement. So for each aspect, I will start from motivation, from why we need to do this, and then I will introduce what we propose and what's the result. And afterwards, I will summarize my talk. So biometric system is an automatic pattern recognition system to verify or identify a user by using his behavioral or physical characteristics such as face, fingerprint. So in general, there are 2 types of the biometric systems. One is the verification system, which is to conduct a 1-by-1. So you and the people present his biometric, and then we retrieve the biometric data, which is pre-stored in the database, and then do a 1-by-1 comparison. This is the verification system. The second one is the identification system. The identification system, we need to conduct N comparisons. So we need to answer a question to establish the identity for each person. So I'm asking who is this person. So the result from the identification system is like a user's identity, or this user is not enrolled in the database. The result from the verification system is a binary result. This person is the one he claims or not. So my focus is on identification system. So if we look a little bit deeper, this is the block diagram. We can see different modules for biometric identification system. We start from if a person presents, we need to collect his biometric data and data acquisition, and then based on this sample or the data we captured from the person, we need to do some pre-processing, and then we create some template, and then we enroll this template in a database. And during the identification stage or authentication stage, we have the same procedures: data acquisition, pre-processing, template creation, and then in this case, we need to do searching by using this user's biometric data. So for each module, we will talk one or several research aspects. First one for the data acquisition. I think for data acquisition, the most important module is the sample quality control. As we can see, these are the 5 samples captured from the 1 finger. But from the appearance, we can see they have different rotations, and also for this sample, it has only partial finger from the presenters. So also the quality for this one looks not as good as this one, or not like this one. So for the pre-processing, after we capture the sample, we need to do some pre-processing. So we start from the segmentation. We need to extract the interest of the area we want to use. So we need to segment only the fingerprint area. So otherwise we will detect some features from the background or because of the noise. And after that, we will estimate orientation field. Then we will have enhanced samples from the previous. So because from this one, we will have it's easier to extract features in order to have a robust template afterwards, especially for the low quality samples. Pre-processing is more important. After this pre-processing, we will have like a better appearance for the captured sample. Then we can extract some robust features. For instance, the most robust features we use in the fingerprint recognition system is called minutia. So minutia is the ending point of the read, also at the point which a single read split into two reads. So based on this minutia point, afterwards we can do template comparison or enrollment. This is the example we compare the minutia. This one we can, if it is a reference sample, this one is if it is a probe sample, then we can compare the minutiae from the two different samples. But the point is that sometimes comparing minutiae is not so easy or robust, because sometimes we will have some minutiae are missing. So, and also sometimes we will have some fake minutiae. So because of the noise. So instead of directly comparing on minutia point, we will extract some robust features based on these minutia points. So we will talk about these robust features based on minutia in the slides afterwards. So a PhD program is not enough to cover all of these research aspects. So we selected three from this. The first one is we did a finger photo quality assessment. The quality assessment for the fingerprints as shown in the right side has been extensively studied by the Martin Olsen, who graduated last year. So we can see from these two samples which were captured by smartphones, and the right side is the fingerprint samples captured by the professional sensor or by the contact sensors. So we can see they have very different appearance. So for the samples captured from the smartphones, they have complicated background, and also the focusing issues. Sometimes we don't have it. It's harder to focus on the finger area. So we need to assess the quality for this sample. Otherwise, if the quality is too low, the performance, the accuracy performance for the system may be low. So we did some experiment. Also, we observed some features. So we did for instance, we use the autocorrelation and FFT, and on a think area, like we consider it's a high quality fingerprint area. So afterwards we can observe that they are regularly peak points, and also there's a very high peak point after FFT. But for the background block and for the low quality block, they don't have such features. So based on this observation, we can extract some features to identify whether it is a high quality block or it is a non-high quality block. So this is the approach which we propose. So we have a training stage. So this is a supervised training stage. So we have qualified blocks, which we consider is high quality blocks. Then we extract features and labeled as one. And then we also have a non-qualified blocks, which consists of background blocks and the no quality blocks. And then we label it as 0. And then we feed into SVM. Then we will have a classifier. So during the assessment stage, we divided an input image into a set of blocks, and then we extract features from each block, and then feed this feature into the SVM classifier. Afterwards, we will have a binary decision for each block. Then we will count how many qualified blocks from this, and then we will do a decision fusing to generate a quality score for this sample. So this is the two samples. We marked out the high quality blocks. So then we will simply count how many blocks marked in this sample. Then we will consider this is quality score for this sample.
How you did this?
How to mark this one?
Yeah.
So this is based on this for each block. For each block, if the result from the classifier is 1, we will mark this block.
I mean the finger itself. You're saying that there are marks in the finger? The picture?
No, this is just an illustration. We mark and the finger area. So the first we divided this sample into different small blocks, and then for each small blocks we extract feature.
Okay.
And then the classifier will tell us this feature will be labeled as 1 or not. It's like will be give a result, a binary result.
But this is a photo of a finger. There's nothing in the finger itself, because from here I can see that there are.
Yeah, the whole picture is a photo of the finger.
Right.
Yeah. So I want to what we do is we want to qualify. We want to figure out this area. Because this area is like the interest of the area.
Thank you.
Yeah. For like this area is like for this area, it doesn't have so many like rich information that we showed previously. Also, it's the same. The input is like the finger photo from smartphone, and then we will divide it into different small blocks, and then we will find out these blocks are from the classifier. They consider these blocks maybe it's a fingerprint area. So the second one is the fingerprint indexing, which is, I think is a crucial techniques for the large-scale fingerprint system. So why? So first we look at some notable large-scale applications. The first one is the UID of India, which already enrolled more than 1 billion people. And for each people, the 10 fingers are recorded in the database. The second one is the US visa program. If you have already visited the US, you need to present your 10 fingers during entering the US. So the third one is the EU visa information system. So far, there are over 20 million applications processed. This doesn't mean there are 20 million fingerprints have been recorded. But since last year, since October, every applicant is required to present his fingerprints. So I think it will be soon to reach at this point. The first one is the FBI fingerprint database, which consists of more than 104 million subjects. So if we want to do a comparison, we want to compare the probe sample, which needed to be identified against all the subjects enrolled in the database. let's imagine how long time we need to get the result. We will use an example to explain this. Let's use FBI fingerprint database. There are more than 104 million subjects and 10 fingers are recorded. So we have the 1.4 billion fingerprints in the database. And on the other hand, neural technology, which is a very good commercial product for fingerprint recognition. So from the website, the comparison speed could be up to 40,000 fingerprints per second, but under a maximize the matching speed scenario. Maximize the matching speed scenario, it means they need to extract templates from the raw samples first, and also maybe they need to load these samples into memory, so they can reach this point. But still, if we want to compare all the fingerprint in the FBI database, it will take more than 7 hours. So we need to figure out something to reduce this response time. So a natural thing is naturally if we can reduce the searching space. For instance, if we know the nationality, know the race, know the height of the subject, we can reduce the searching space. But unfortunately, these information are not always available. For instance, if we got a fingerprint from a criminal scene, so we don't know any information from this. This is actually the latent fingerprint. We only have this latent fingerprint without any extra information. So we have to only use biometric data, fingerprint data to do searching. So another way to reduce searching space, which is called fingerprint classification. So by looking at this, some global information from fingerprint, for instance, if we look at this sample, their rates enter from the one side and rise a little bit, and then go out from the opposite side. So we call this sample, we classify this sample as arc fingerprint, and also have the left loop. Their rates enter from left side, and then curve back, and go out from the same direction. So this is the left loop, and also we have the right loop and the wall. So we can classify this original fingerprint into 5 subsets. So in this case, we can reduce some searching time. But there are 2 major drawbacks. The first one is the number of these classes is limited. So there are only 5, but maybe you can get more, but not as many as we want. The second one is the distribution is not even. So like over 90% of the fingerprints are distributed to the left loop, right loop, and the wall. So what do we want to do? So we instead of only considering these global features, we needed to look deeper. We look at the minutia point. So as I introduced this like a deeper information from if we look at this global level. So we will extract some robust features based on this minutia information. Also, sometimes we use the local rich information around each minutia point. In this case, we will have some robust features, and then we can classify these features into a set of classes, maybe as many as we want. So the basic, at least a brief structure where how we use fingerprint indexing in a large scale fingerprint system. So we have enrollment stage, we have reference sample, then we do feature extraction, and then based on this feature, we do classification. No, not the exact classification. We will enroll this sample based on these features, and to build an indexing space. And then for the probe sample, we do the same feature extraction, and then we will retrieve the corresponding sample, which is stored in the database. Maybe they are not in the database. So as we can see, so the whole purpose for the fingerprint indexing is very simple. It's just to reduce the searching space. If we can reduce the searching space, of course, the whole comparison time, the response time will be reduced. So the feature extraction, it seems the critical component for fingerprint indexing approach. Then what we have done, we designed 3 fingerprint indexing approaches based on different feature extraction methods. The first one is we look at the user information and also the local reach information to extract some decimal features. This is our first approach. The second one is we only focus on user information, because the reason is that the user information is standardized in the ISO fingerprint standard template. If we only focus on user information, the interoperability of our algorithm will be better. The third one is we focus on extract binary features, because the reason is that if we performing on the binary features, it potentially should be faster than performing on the decimal values. So these are some information in details about each feature extraction method. The first one is the decimal feature based on user and the local reach information, as I mentioned just earlier. So the first one, we extract some geometric features based on a triangle formed by 3 users. Because if even we have some rotation, but maybe the area of this triangle is consistent. If you have some rotation, the area is consistent. Also the user direction, if you have a rotation, but the difference between 2 user direction is still consistent. So we also look at the reach curvature. So from at the center of the fingerprint, the reach curvature is higher than the reach curvature close to the edge point. And also we look at the reach density, as you can see from there are 2 blocks. One block is here, another block is here. So there are more reaches in A block and then in the B block. So this information can help us to create robust feature. The second one, we just look at the minutia information. So we form a local structure which is called a minutia vicinity. So we use 4 minutia to form a basic structure, and then we define 6 orientations. Based on each orientation, we will align another 2 minutia to each orientation. Then we will have a new aligned minutia. So in total we will have 12 newly aligned minutia. Afterwards, we will do a Manhattan distance, and also we will combine the location information and the direction information to construct a feature vector consisting of 24 components. Then we will use this feature vector for the indexing space creation. The third one, we develop a binary features. The binary features, the idea is that we consider a malicious disk. So because it's really hard to find out a reference point for the whole fingerprint. Sometimes because of the noise or something, some people consider, yeah, this is a reference point maybe for this sample. But to find out this point accurately is not so easy. So what we do, we will consider each minutia point as a reference point. So for instance, we will consider minutia mi is a reference point, and then the rest of the minutia points included in this circle will be aligned to mi. So afterwards, we will have after this local alignment, we will have 3 attributes for each minutia. So before generating this binary, we will initiate a k-bit binary vector with all the components set to 0. So then this is a classification stage. So we assign each minutia point to it. There is the 3 clusters according to the Euclidean distance. Why we assign to 3? Because the variation, because of the variation from the samples. So if we assign to 3, maybe the binary feature we generated will be more robust. So after we have this binary feature, or if we need a minutia point assigned to this cluster, then we will flip 0 to 1. But only so, but there are maybe more. There are more than 1 minutia point will be assigned to the same cluster. But in the end, it's only the first one take effect. So after proposing the approach, we need to evaluate the performance. So this is the 2 metrics defined in the ISO standards to evaluate the performance for fingerprint indexing. So let's recall the whole purpose for the fingerprint indexing is to reduce the searching space. The output from the fingerprint indexing is like a short list of candidates. So this short list of candidates afterward will be used for the verification algorithm, or maybe used for the human experts for manually verification, for manually checking. So this short list should not be large. So this penetration rate relies on the number of these candidates. And also there's another metric, which is the pre-selection error. So when an error will occur, for instance, if I am enrolled in the FBI database and somebody used my fingerprint to do searching, and he used the fingerprint indexing approach. So he will generate a short list of candidates by using my fingerprint. I think he expects my fingerprint will be, my ID or my fingerprint will be presented in this short list of candidates. But sometimes if the fingerprint indexing approach is not good enough, maybe I'm out of this short list. So in this case, a pre-selection error occurs if I am not included in this short list of candidates. So in the end, we will count how many pre-selection errors for this fingerprint indexing. So in general, a good indexing approach will expect lower penetration rate. It's short, the list of this candidate shouldn't be too long. And also the error rate should be lower. So we evaluate our approach and public database in order to compare with the existing methods. We compared our approach to one of the state-of-the-art fingerprint indexing approach. So the line close to the original point, obviously is better. It's the penetration rate and the pre-selection error rate. So actually, this is the performance from our approach. So it seems better to the one of the existing state-of-the-art fingerprint indexing approach. So the third topic which I was working is related to security. Yeah, we have limited time, so because the security is important. Last year, maybe you know, 5.6 million fingerprints was stolen in US, and recently there's another incident which put 55 million fingerprints in danger in Philippines, which happened just last month. So if you put stored all the fingerprint data in one database, this will be a high-value target. So we need to do something to protect our template. The first one, we propose a template protection method based on blown filters. This is the main idea of the blown filters. If we have a binary template, we will map each column to one location in a blown filter result. So for each column, we calculate the decimal value, and then we will flip the original one for original 0 to 1 if there's a column is assigned to this location. So in the end, maybe there are two columns will be mapped into the same location, but still will remains 1. So in this case, it's really hard to reconstruct the original binary template. So based on this idea, we applied a pre-alignment. It's a very simple idea. So we only consider we detect a reference point for each sample. We only consider the malicious point inside this circle, and then we will generate the binary template, and then we will using blown filter based on this binary template. So this is the performance for this template protection method. We can see comparing to the method without using blown filters, we don't have so much equal error rate decrease. So we don't decrease so much performance. The last one, we also developed a secure fingerprint indexing by proposing an encryption method before a binary representation generation, before generating the binary template. So in this case, all the information stored in the database are encrypted. We can see we don't have any original biometric information stored in the database. This idea is based on a standard encryption algorithm. So which means our security is guaranteed by a standard encryption algorithm rather than by the biometric system, not like the blown filter template protection method. That's it. So afterwards, we also evaluate our performance between indexing approach without considering security, also compared with this secure fingerprint indexing approach. So from the result, we can see we don't have the performance doesn't decrease. Also, we remain more or less the same level as we do in the plain text domain. So we also have the chance to evaluate our algorithm in a large-scale synthetic database, which consists of the 250,000 subjects as a reference and 50,000 subjects as the probe. So we still remain very good performance as we achieved in plain text domain for the fingerprint indexing. So that's all. And the summary, the summary is we proposed the finger photo quality assessment approach. Now we have the 3 fingerprint index approaches, and also we did security. We proposed the 1 template protection method based on blown filters, and also we have a secure fingerprint indexing approach. Yeah, that's all. Thanks.
I always like to have a 25 minutes presentation and 20 minutes discussions. This is why.
Yeah, thanks, but
We started 2 minutes after
okay, so
12:15, so it's not that bad.
Okay.
yeah, I would like to report what I have done during this period, and then maybe it's like a little child lecture on defense. So I will use the opportunity to practice for the
Oh, for
defense.
the defense.
Present,
You're gonna try
yeah.
defense now. Okay. Well, let's try to get some trial defense questions then.
yeah.
So,
Well, I have a couple of questions.
Yeah.
Did you consider errors because it is not possible to repeat the same fingerprint at enrollment and
Exactly.
at identification. In this case, you say you focus on identification, but the same holds for authentication. So there will always be a difference.
Yes.
Now, your feature extraction methods are pretty complex. So they involve a lot of points,
Yes.
these circles and triangles and all that. So I'm afraid that requires that the quality of the fingerprint sample that you collect must be extremely high. Otherwise, you will not be able to compute that measure.
Yeah, that's the reason. We.
Something like this.
That's the reason we consider locally. It's because the fingerprint, the biometric system is always like a similarity between 2 samples.
That's why I'm asking.
Yes. So in this case, but for sometimes these parts are missing, or the quality of this part is not good. But sometimes there are some parts the quality are good. So I just consider extract feature from this only small area. So they will have some parts which are good enough from if this sample is from the probe sample for the identification, there's one enrolled in the database. Maybe there are some parts are quite similar, but some parts are not.
Sure.
Yeah. So what I will propose is we consider locally, not like yeah, of course the missing minutiae, also the fake minutiae always happens. That's for sure.
That implies my next question, which is about the efficiency of this. So if you have to search for areas that are or of enough quality to compute all this, how long will it take to identify a person?
To identify a person?
Yeah. So did you measure this in your experiments?
In experiment, we didn't measure how many times, because time relies on so many aspects. The idea is that for the fingerprint index, the idea is that if you can reduce the searching space. So for instance, I divided the whole database into 2 parts. I only focus on the first part.
But I think it would be worth measuring because a complicated feature extraction requires longer processing time.
But this feature extraction method is only where, for instance, only happen during the identification stage. Because for the enrollment stage, that's the offline stage. All the features already extracted in the database.
Yeah, but when you collect, when you want to identify, you will have to extract them.
No, not identify. I need to extract. No, not from sample.
Okay, how can you compare them?
No, for the identify, I only extract from only one sample.
Okay.
For only one sample, you can see from the So for the reference sample, like for all the features already extracted in offline states and then it's stored in the database. But for identification, if you have only one sample, I just do once. Not all the raw image installed in the database. That's not. We store the features extracted from the samples, so it already stored. Not raw images. Raw images, that's not allowed usually. Yeah.
Okay, I will have more questions, but I don't want to be the only one that asks questions, so we can take that later.
I guess that's nobody else who has questions. Yeah, there's one.
Just actually an old question about the synthetic database.
Yep.
Yeah.
The synthetic.
And we have some discussion also in the project fidelity, and also always people are concerned about this case because this is a synthetic database. How can you convince other people the same method will be working on the real database?
Yeah, this is like not a perfect way to compare because the large scale real fingerprint database is almost impossible to obtain, to get that.
Can you use the Philippines ones?
Okay, if I have. Yeah. So yeah, that's a good question. So it's it's really hard to say this point. And also, yeah, that's true. And also the synthetic database samples, the quantity looks not bad, but quite good because what they form this synthetic fingerprint because the first point they were located at a minutia point at a different place. Afterwards, based on minutia, they will construct the ridges. How to convince as good as in real fingerprints? It's really hard to compare. I would say just give an impression on this large scale data set, not. No, I don't. We don't have the experience and the real large scale database. It may be worse than in the synthetic, but maybe in a large scale. But that's what we can do from the academic area, I think. There are some large scale database in the real scenario. They are from the police department, but we cannot do that, maybe publicly at least.
Next research.
Now you could convince police or the owners of the large database to calculate some properties and compare those properties to the synthetic database properties and say, because those match, we are more likely to have a representative synthetic data that mimics the real world data. Actually, they don't need to give you the data, they don't need to run your stuff on it, they just need to calculate like some properties of the database
that actually have already happened in the fidelity projects, but still some people are not comfortable with this.
I think so. Because of the rules, you know information from this large scale database from a real fingerprint. It still needs some information for the people's biometric data.
Yeah.
That's even they discuss even if we send our algorithm to their location to run, still it's really hard to do this. Because you use the algorithm, you can learn something from this database, right? At least if it works, then you say, oh, my information in this database is not like this way. I need to try something different. So if you want to use this real, it's like regulations issues.
Yeah. Yeah, I had a small follow-up on Slobodan's question on approximate search, whether your methods can give because you're pre-selecting some of the candidates.
Exactly.
But can you give me order? Can you give me the confidence?
Yes, there's order for each one. There's a similarity score for each one.
Right.
So we sort this one, we select the top similar candidate.